Welcome to This Explainer. If you're just starting to look under the hood of artificial intelligence, it's super easy to picture it as this abstract, magical brain, just floating out there in the cloud somewhere. But today, we're going to ground that idea in physical reality. We're diving into the actual energetic cost of an AI's thoughts. And we'll see exactly why just building bigger and bigger systems, well, it might not be the answer anymore.
So usually when we hear about the limits of AI, it's all about, a shortage of computer chips or maybe running out of raw mathematical power. But what if there's a completely different threat lurking in the background? What if the real danger to AI's growth isn't doing the math itself, but the massive physical burden of shuttling all that information back and forth across these vast networks of hardware?
To really wrap our heads around why this is such a massive deal, we kind of have to look at how we got here in the first place. For over a decade now, we've basically been operating under this very specific illusion. We believe that intelligence is mostly just a matter of arithmetic volume. Progress in AI basically had one simple rule: make it bigger, right? If you wanted a smarter AI, you just needed more chips, larger data sets, bigger models. The whole thinking was if you just threw enough raw computing magnitude at a problem, its capability would naturally rise. And honestly, for a long time, that actually worked.
But we've hit this absolutely crucial turning point. As highlighted by AI pioneer Jeff Dean, when we get to extreme scale, an AI system isn't just sitting there calmly calculating. Not at all. It's desperately trying to coordinate memory, route intermediate steps, and sustain these absolutely massive flows of information across its physical infrastructure. It turns out, the model isn't just some abstract math concept floating in the ether. It is a highly energetic system, deeply embedded in real, physical hardware.
And here's where it gets crazy. Doing the actual math, that's become relatively cheap and abundant. But the system is literally exhausting itself just fetching, moving, and synchronizing that data across global networks. Let's think of it like a massive restaurant kitchen, right? Chopping the vegetables, which is our computation, is incredibly fast and easy now, mainly because we have so many chefs. But the kitchen is completely failing. Why? Because those chefs have to run a mile down the street every single time they need to fetch a single carrot from the fridge. The bottleneck has shifted completely away from doing the work to just moving the materials.
So the whole cost center of this operation has completely migrated. A basic multiply-add operation, the fundamental math of AI, that's now just a tiny, tiny slice of the pie. The massive, overwhelming energy drain actually comes from pulling that data out of memory, physically moving it to the processor, and then writing the results back. And here's the kicker. The larger the AI becomes, the more frequently it has to pay this massive transport cost. It really adds up.
Okay, so what happens when engineers try to fix this bottleneck simply by making those data transfers faster? Well, the natural response, of course, is to build better interconnects, shorten the physical path, reduce latency. Basically, they try lowering the resistance on the roads to make things smoother. But doing this introduces a fascinating concept called the efficiency trap. And it warns us that simply making the roads faster can actually, ironically, lead to much worse traffic.
Now, you might assume that reducing resistance just outright solves the problem. If it costs less energy to move a piece of data, we should be saving energy overall, right? Makes total sense. But actually, no. We fall right into this really dangerous amplification trap, because we have to look at what human behavior and system architecture actually do when a resource suddenly becomes way cheaper to use.
Let's break down how this builds step by step. Step 1. Engineers successfully make those data transfers cheaper, which reduces the individual cost per action. Awesome. Step 2. Because it's cheaper, developers go crazy and deploy the AI wider, using it for way more things. Step 3. This massive, wider deployment spikes the total request volume absolutely astronomically. And then, Step 4. The entire system pushes right back into total flow congestion. So cheaper paths just lead to more usage, which ultimately creates even more total data movement. It effectively takes a huge win in efficiency and turns it into this uncontrolled, unsustainable expansion.
To actually fix this, we need a completely new rulebook. We call this the energetic paradigm. Instead of just building a massive brain first and, worrying about the power bill later, this totally flips the script. It demands that we put physical flow before scale. Under this new rulebook, an AI architecture isn't even considered legitimate until its physical flow structure is properly bounded and justified from the very beginning.
Now, to actually pull this off, the system relies on a few core principles of what we call energy flow governance. Ultimately, strategies with fancy names like local decision first and deferred synchronization, they all serve one main goal: allowing subsections of the AI to just do their work internally without constantly phoning home.
It absolutely stops data from traveling these huge, long distances when it simply doesn't need to, and it totally avoids pinging the entire network just to update some tiny, unimportant detail. Seriously, think about how a lot of current AI works today. It's literally like calling the global CEO of a massive Fortune 500 corporation just to get approval to buy a single paperclip. It is just an incredible waste of high-level energy for a super simple task. That principle I mentioned, local decision first, fixes this by ensuring the AI handles simple, low-risk queries locally. It prevents the system from constantly waking up this entire energy-hungry global network unless the decision is genuinely complex or highly uncertain.
But, of course, without real metrics, all of this is just a fun metaphor, right? To actually govern an AI system this way, we need a hard way to measure it. So the energetic paradigm introduces operational constraints, basically a set of vital signs to monitor the AI's actual physical viability. We're not just talking about speed or accuracy anymore. This is literally about whether the system can sustainably survive its own massive growth.
To really track those vital signs, we have to look at a few key things. First, we have to measure the sheer complexity of the data flow just to see what is actually moving around in there. Then we need to check how much actual, useful intelligence we're getting back for the physical energy we're spending. It's like asking for our return on investment. Next, we have to ensure our efficiency gains aren't just causing way more traffic. Making sure we avoid that amplification trap we talked about. And finally, we must track how often parts of the system are just sitting around, left waiting on each other. Together, these metrics give us a clear picture of how AI absolutely must be governed by its physical toll. Let's actually look a bit closer at that last one for a second. Synchronization. In a massive AI system, when one part is forced to just wait around for another part to finish before it can move forward, that is a huge vulnerability. If everything depends on everything else, a small bottleneck cascades, and suddenly it makes the whole AI system structurally fragile. High synchronization is not just some annoying technical delay, it's an absolute foundational weakness.
So ultimately, this whole thing boils down to one simple but highly disciplined question. Instead of just asking if a calculation can be made a little cheaper, or if the hardware can tolerate just one more data transfer, the energetic paradigm demands we ask, is this flow required? Before a single piece of data ever moves across the network, the architecture must completely justify that movement. That is a massive shift. We're going from just trying to optimize an existing mess to structurally governing what is even allowed to move in the very first place.
Because under this new paradigm, the whole concept of intelligence is totally redefined for us. A smart AI is no longer just the one with the biggest parameter count or the most raw mathematical scale. Not anymore. True, sustainable intelligence is capability that's generated through governed, localized energy flow. Basically, it's an AI that is smart enough to know when not to move energy through its whole structure.
And that brings us to the ultimate crossroads for the future of this amazing technology. As we watch artificial intelligence infrastructure continue to scale up and embed itself deeper and deeper into our physical world, it leaves us with this final, really provocative thought to consider. Are we just going to keep building systems that endlessly reproduce their own traffic jams and energetic bottlenecks? Or will the future belong to those who can actually master the flow and elegantly reorganize the physical pathways of machine thought? Thank you so much for joining me on this explainer. I really hope this gives you a completely new lens through which to view the very real, physical reality of AI.